Now let's consider sigma notation in linear algebra. Now there are lots of sums in linear algebra, so there's a lot of room for sigma notation in this case. Okay. For instance, if you know how to multiply matrices, the rule is you multiply rows times columns. The resulting matrix here is going to be a 3 by 2 matrix. Why is that? Because the left matrix has 3 rows and the right matrix has 2 columns. You also need to check, by the way, that the number of columns of the first matrix are equal to the number of rows of the second matrix, which they are. Actually, we can do this. This is 3 by 2. I'm sorry, 3 by 3. And this is 3 by 2. Now you need to check that these two are the same, which they are, and the result is going to be a 3 by 2 matrix. You can do this in general for any two size matrices that you're multiplying together. So here we have our 3 by 2 matrix. Here's the first term. Here's the first row, first column means I take the first row of the first matrix times the first column of the second matrix. And I multiply corresponding terms term by term. A11 times B11, that's this one here. A12 times B21, that's here. And A13 times B31, that's here. I'm not going to do through this anymore. If you need review on multiplying matrices, then there are many resources that you can look at. Now the point is that we would like to write this in summation notation. Look at the indices involved here. Notice that the second index of the A is always equal to the first index of the B, no matter where you see it. And that these two indices run from 1 to 3. Here's 1, 1, 2, 2, 3, 3. And you can find that in every single entry. 1, 1, 2, 2, 3, 3. Right? Now what about the other indices involved? Well, look at this one, for instance. A21B12 plus A22B22 plus A23B32. In all cases, the first entry is 2, and the last index is 2. Sorry, the first index of A is 2, and the last index of B is 2. 2 and 2 here, 2 and 2 here, and 2 and 2 here. Now, where is this entry located? This is the 2, 2 entry. So you see the first index on the A determines the index of the location in the final product, and the last index of B determines the row index of the location of the product. Okay, so how are we going to systematize this? All right. Cij is the ijth position of the product. Now what we said was that the ij corresponds to the first index of A and the second index of B. And the inner indices have a sum from 1 to n, where this n is the number of columns of A, and it's also equal to the number of rows of B. All right. So this very nice compact way of writing the entries of the product matrix in summation notation. All right. Here's another example. And here's some exercises for you to practice with other matrices. Okay. And you'll show that matrix multiplication is associative. Some special matrices you may be aware of. This is the identity matrix. It has 1s on the diagonal and 0s everywhere else. Now, you can do this using summation notation with the following symbol. There's a special symbol called the Kronecker Delta, and it's a symbol that's equal to 1 if the first index I is equal to the second index j, and it's equal to 0 otherwise. So delta ij is actually equal to the ij entry of the identity matrix. Right? Because the identity matrix is 1 on the diagonal, and that's the case when the row index equals the column index, and it's 0 otherwise. Right? Now, this is an interesting problem to show that the delta ik times delta kj equals delta ij. There are a couple ways you can do it. You could do direct, or you could use matrix multiplication. You have to think, what matrix multiplication does this correspond to? And the hint is that delta corresponds to the ijth entry of the identity. Okay. Another common matrix operation is the so-called transpose. For instance, if I take this matrix 1, 2, 3, 4, and I take its transpose, well, the rows become columns and the columns become rows. So that the first row here becomes the first column of the transpose. Second row becomes the second column of the transpose. So what's happened here? I've switched the rows and the columns. So the ij entry of the transpose matrix is equal to the ji entry of the original matrix. So I can say ij of transpose is equal to ji of the original. Okay? Now here's a formula you've seen in linear algebra. To multiply two matrices and take the transpose is the same as taking the individual transposes and multiplying them in the reverse order. Right? And you can see this step by step. We have this expression for the ij entry of the product AB. Now, if we take the transpose of that matrix, we're going to switch the I and the j. That's all we're going to do. The only difference between this one and this one was we switched the I and the j. Okay. Now, what about AJK? AJK is the KJ entry of A transpose. What about BKI? BKI is the IK entry of B transpose. Now, we'd like to think of this as a matrix product, but it doesn't match up. However, if we reverse the order, so here's where the reverse order comes in. If we multiply these two terms in the other direction, that's okay because this is a number and this is a number. These things are not matrices, these are individual components of the matrix. So I can multiply it this way or I can multiply it the other way. If I reverse the order of these two factors within the sum, I now get a summation that looks like a matrix multiplication. And in fact, this result is the ij entry of B transpose, A transpose. Okay, so that's a way to prove transpose identities using summation notation. So here's an exercise for you. And here's an exercise that relates to the functions chapter, where so you want to tell whether transpose defines an invertible function from square matrices to square matrices, or whether transpose defines an isomorphism on these matrices. Okay, and here, when you say this GL to GL, this means with multiplication. With matrix multiplication. Okay. right? Another important aspect of matrix is a so-called trace. The trace is equal to the sum of the diagonal terms. Trace only applies to square matrices. If I have a square matrix, like if I have down the diagonal 1, 2, 3, and I can have anything else here, 4, 5, 6, 7, 8, 9, the trace of this is equal to the sum of the diagonal entries equals 1 plus 2 plus 3. The general formula for trace, well, if we write out the individual terms, it looks like this. But if we write as a summation, you're just summing over a's from 1 to n. You can see that if there's an n by n matrix, there will be n entries on the diagonal. So sum from 1 to n of aii, row index equals column index. All right, now there are many properties of trace that you learn in linear algebra, and you can prove these using summation notation. All right, now consider the trace of the product of two matrices. All right, trace of the product. I have to take the sum of the diagonal entries of AB. Now I know that AB, if I take the ith entry of AB, what's that? That's going to be the sum. Now remember, the first index on A is the first index in the product, and the second index on the B is the second index in the product. So we get this sum from k equals 1 to n. But now I'm summing over all the diagonal entries, so I have to sum that from I equals 1 to n. So that's where this expression comes from. Sum I equal 1 to n of the sum from k equals 1 to n. Now just for jollies, let's consider the trace of AB, trace of BA. And you'll find that you in fact get the same, well, let's do this. You get something like this. Now, we've done exchange of summations before, and in this case, because the limits don't depend on the indices, we can simply exchange the summations. And we can also exchange the entries within the product, because this is just a product of ordinary real numbers. And we can rewrite this trace, exchanging first the summation, and then changing the order. Well, all right, first changing the order and then changing the summation. We find out that we end up with something here that looks very much like what we had here. The only difference is that the I and K are exchanged. But I and K are just letters to indicate an index. So I could replace these I's, all these I's with K's, and all these K's with I's. So if I take this and I exchange K with I, which won't change anything, because those are just indices, if I exchange K's and I's, I will end up with this term here. So what's the point? We've shown that the trace of AB is equal to the trace of BA. All right. So we have some exercises with traces. And that's the end of this section.